And the other part of this PDF page is the interesting way that people are taught to decide very quickly on what symmetry group a molecule obeys. If you take a group, then you may start wondering, oh, I have to identify sigma V plane, I have to do this. So here they have given a flow chart. This is the sequence in which you will go, and you can quickly arrive at what is the symmetry group of the object you are looking at. Start with, does the object have a rotation axis? Well, it doesn't, then it falls into those trivial groups. If it does, well, then look, does it only have an improper rotation axis? So it may not have proper rotation, you may have to have reflections, then it becomes SN group, but it does have regular rotation axis, then you come to this and so on. So you go down the flow chart, you get all the groups. So for example, if you just went down this saying it has proper rotation axis, is it a linear or special? No, let's say you have ammonia, so it is not. So you come down, does it have n C2 axis normal to Cn? Well, ammonia may not work, but then suppose the answer is no, then are there horizontal planes? No. Are there any vertical planes containing axis? No. Then you would get Cn. If you don't have any other symmetry elements, you would have plain vanilla Cn. If you have other ones, then you will get shunted into CnH, CnV and so on. Similarly, if it has perpendicular plane which is bisecting which is perpendicular to the z-axis, then you will get the DNH and DND, etc. And if there are no dihedral planes, then you will come to plain vanilla Dn. So this is an interesting way of thinking about how to quickly go down a option chart tree to decide the symmetry of a molecule. Okay, so much for this. You can continue to read this transparency if you like it. And second half, so I think this was a D3 example. Yeah. So this I was waving my hands about. This is C2H6. Oh, and this is the so-called obscured ethanol, because the two H's are just above each other. This is an example of a pure D3, because there is a plane perpendicular to this which maps this into this. There are of course this planes that pass through. Oops, no, I'm sorry, I'm reading this wrong. So there is this hydrogen which is, let us say, towards us in this ring, but then in the bottom one that the hydrogen is in the behind the. So this is actually the case of having to rotate and then reflect. Let us go to the Otterbein and check quickly a few of the things, then I'll come. What I want to do for completion is the proof of normal subgroup giving rise to a factor group. Okay, so maybe we'll do that first, and then so actually we could as well, since you can always look up those molecules on the animations yourself, it's not so difficult. Let us go through one example in some detail which will illustrate what we have been doing. So S3 is the smallest non-trivial permutation group, permutation of 3 elements, but it is permutation group which is also the group of the triangle, equilateral triangle, including reflections, including . So we have its geometric center around, and so if we designate these A, B and C, then of course we have 2 pi by 3 rotations, and so there are 3 elements, but additionally we reflect in these planes. So those reflections exchange A and C or exchange A and B at a time. By allowing all of these, we have effectively allowed all the permutations of 3 objects. Okay, so the group is isomorphic to S3. So let us write down its elements. We can write them as matrices, which sometimes comes out useful, but we can also remember them. So I will use a particular notation for this, I mean particular way of listing these. Suppose we call E, no, this is too thick, E the identity, so let us call I to be the improper rotation or the flip, so 1 minus 1, and then we will write down this A and B a little bit later, and we write C and D. So this C and D we take to be our usual 2 pi by 3 rotations. So they have cos 2 pi by 3, and I think I am writing this correctly, square root 3 by 2 and minus square root 3 by 2, and then here it will be half, half and minus square root 3 by 2 and square root 3 by 2. So this is 2 pi by 3 rotation, and this is 4 pi by 3 rotation. Now we have to, so this I go to this basically will, so these matrices act on xy axes, okay, and we are claiming that these are symmetry elements, but they have a correspondence in this. So I is the one where only one of them something gets flipped, is an improper rotation. So now we combine these proper rotations with the improper rotations. So it basically, one way of thinking about it is we change the signs of these in one row, but not both. This is what will happen if you say multiply by inverse of this, which is minus 1, 1 here, okay. And so there we change the, and here we will change the signs of this. Yeah, I think we can use this. So E, then A has, so his is C, has a minus 1 in the upper corner and 1 lower corner, so that will do. And we can compare the proper rotations. So this is a proper rotation, oops, with minus sign. This is a very strange way of writing. See, for an orthogonal matrix, you must have sine theta and minus sine theta. There must be opposite signs here. But then I would have cos theta and cos theta on the diagonal. So this is also not what I like. We will live with this, okay, you can check that this is correct. So we have this cos theta on the diagonal, and off diagonal we have minus signs, and then we should actually have multiplied by this, and that is the only thing I am not sure of. Probably I have multiplied by minus 1, 1, okay. You can check it later. Now let me just tell you that if you start with this, we can prove a few things quickly. So, exercise, identify subgroups. So, I think the only change I have to make here is put minus up here and make this plus. Then this is correct representation of the group. The other ones are equivalent sign changes, but this is fine. The one in the slides is fine, but it's not what physicist will write. So, this is fine, because then you can see this inversion thing times C exactly reproduces A. So, this row into this column gives minus signs to the top row, and the lower rows do not change. Similarly, this into this gives minus signs to these and does not change the lower one. So, I think this is fine. So, this set of matrices will form a group. So, I think this is now correct, I am happy with that, and actually then it tallies with this minus 1s, minus 1 up, yeah, now it tallies completely with Horn's way of writing. Now, the thing is, we identify the subgroups. One of them is just E and I, and the other one is E, C and D. In fact, I should have written capital E, but now you ask, so as exercise I would say calculate the cosets, right and left. Okay. So, what would we get? So, we need the multiplication table for that, which you can put in the corner, and I am really running out of time. So, this I meant to do as a class exercise, but let me go and prove the theorem that we wanted to prove about normal subgroups. So, here it turns out that if you do this, then check that ECD is a normal subgroup. So, has right coset equal to left coset, left cosets. So, we will come back to this in a minute. We will let us do the abstract part first, which is a little easier to do than working out the example. So, we want to check two things. For a normal subgroup, left cosets are same as right cosets. Okay. Now, by definition, we mean by normal subgroup is meant that G n G inverse is equal to n for all G. So, a left coset cosets are formed by G times n. So, consider an example where you say that this is G times some element n1. but what we can do is multiply it by G n1, and I can put a G inverse G on this side. Because of its normality, it becomes equal to some n2 times G, but this belongs to the right coset. Right. If I start with some element G n1, then it is also a member of the right coset formed by the same element G, multiplying the n. So this left coset element is equal to some, the same element of n is obtained through a right cosetting operation and left cosetting operation with the same G. So they basically make sure that all the left cosets will be right cosets. Thus the elements of right cosets and left cosets are same. So this is one property of normal subgroups. This may not always happen, and I meant to work out this, but I am a little poor at working out while trying to lecture. So but we can do it unless you have more time and time to make mistakes which you can correct. The next theorem we want to prove is that the coset space G slash n formed using a normal subgroup n itself carries a group structure. In other words, if the group you are cosetting with was just any ordinary subgroup, then this will not work. But if it is a normal subgroup, then this, so then if it was for a generic subgroup, it would just remain coset space, it will remain some space of equivalence classes. But when n is a proper subgroup, then it carries a group structure, and is called factor group. So here it's a matter of prescribing what you mean by the group multiplication correctly and then checking that it satisfies all the 4 requirements. So we prescribe group multiplication between coset members to be the G group multiplication between its representative members. Between there. So if I have a G1 belonging to C1, which is some coset 1, and G2 belonging to C2, then G1 G2 equal to, sorry, spoiled the line, then C1 C2. So this is a multiplication of cosets is same as so this is coset multiplication or factor group multiplication, and this is G multiplication. So we can see that the various axioms of group are satisfied. So firstly, for closure, clearly if I multiply these two, I will get some, so this has to do with equivalence classes. Equivalence classes exhaust the whole group. Therefore, if I take two representatives G1, G2 and multiply them, the resulting multiplication should belong to some coset, right? So there always exists some coset containing any G1, G2 due to equivalence classes property. Then 2, associativity, that is easy because it is directly inherited from G multiplication. G multiplication. Then we need the existence of an identity. The identity element of this coset space G over n will turn out to be n itself. The entire normal subgroup n is essentially the identity element. As a coset serves as the identity element. Well, one simple argument is to check is that is the one equivalence class which contains the identity element. So anything to multiply by this particular coset, you pick from the representatives the identity all the time, you will get back the same old coset. But I think one can also check that, so one argument is to pick E which always belongs to n, because n is a subgroup, so it has to contain E. So pick E belonging to n as the representative in all multiplications. So I think that is certainly true, but I think you can use the normal, we'll do it in a minute if we have time. And number 4 is inverse. this is where we need to use the normalcy a little seriously, because if I have, suppose I have G1 belonging to C1, I have to now show that there exists some other coset which contains G inverse, so that I get N. So consider the fact that G1 times N is going to be N, because N is the identity. So what I meant was C1 times N is equal to N. So I will put because. So sorry, the other way around. Due to, so because is here. Because G1 times N is N, because the right cosets are itself, the left cosets are N itself. So you get that, what we have is G1 and G1 inverse is equal to N. Okay. So G1 times N is equal to N times some other C2. What we have to show is that so if I take G1 times some N1, its inverse is equal to N1 inverse G1 inverse. And if I have, so there will be another, so this, if I multiply it by any generic element of a C2 which is of this form, because of this relation. So multiplying from the left by G, so what we wanted to show was that there always exists a C2, some other coset, such that, so let C1 be formed by G1 acting on N and C2 be formed by G2 acting on N. Then for C1 inverse consists of elements that are of the form G1 N1 inverse, which is N1 inverse G1 inverse, but N1 inverse belongs to N, so this is of the same form as N times G1 inverse, and so this is a, so we have to convert this into a left coset. So I can write here G1 Yeah, so we have to show that there is some G2 that does that, right? So we insert G2 inverse and N1 inverse G1 inverse. That does not help us directly, but we write this. So we have to show that this becomes an element of the N. So if we are trying to show this, if I have N1 inverse G1 inverse, I will now supply on this side G1 inverse G1, then the G1 inverse G1, N1 inverse G1 inverse is nothing but some other member of the set N, and therefore the inverse of C1 consists of elements of the form G1 inverse times N itself. So the inverse of the, I am sorry, because of the things we are trying to balance, concepts we are trying to balance, you get it's sort of repetitive what you are trying to do, but I think I can repeat it now. It has taken a few minutes more, but so given a C1, this is of the form G1 times N, the C1 inverse will essentially be all the elements of the form G1 inverse N, because the inverse of C1 will, as computed here, will lead to this, which is another coset, a left coset. So it shows that given any coset, there exists another left coset such that it is the inverse in the usual sense, where N acts as the identity. And we use the normal group property here. From here to here is due to normal group. So you get back to N itself. There is some other N1 prime which multiplying this will produce the coset which is the inverse of the C. Okay. So we have checked all the 4 properties of group, and so this establishes what we call the factor group. And this completes all the things that we were trying to do up to now, which has to do with cosets, equivalence classes, and normal subgroups, subgroups and normal subgroups. And we will now go on to representations and characters which are used for classifying the spectroscopy. Okay, thank you for bearing with it.